Today we're looking at piecewise defined functions. A piecewise defined function is a function defined by two or more equations. Each piece of the function applies to a different part of the domain. This is the format for the definition of a piecewise defined function here. You've got f of x, so function notation here equals, and then they give you different algebraic expressions here to represent the various parts of it. This one has two pieces to it, but it's actually not limited to two. It could have two or more. Next to it, they give some restrictions for what x's can be used for each of those pieces there. Now you'll notice that the x values for this piece are unique to the x values for this piece over here. So the first piece includes only x values that are less than or equal to 0. So all the negative numbers and 0. And the other piece includes all x values that are greater than 0, which would be all the positive numbers. All right, the graph of a piecewise defined function for this particular piecewise defined function looks like this one. And you'll notice they've got it split up here into the two parts. So the parts where x is less than or equal to 0 is the function y equals x minus 2, which makes this line over here positive slope with a y-intercept of -2. And when x is greater than 0, it makes this piece over here. Now it says x is strictly greater than 0, so there's an open dot here at the y-intercept where x would be equal to 0. The open dot says that it gets infinitely close to that point, but it actually never gets there. So this side has a slope of 2, and if it was actually allowed to touch the y-axis, it would have a y-intercept of 1. Okay, so if the transition point of the two pieces is evaluated to be the same for either piece, for both pieces of the function, then we would say that the function is continuous. Ended up with a weird line on there. There, made it go away. Okay, so for this particular one, if the two pieces were evaluated to be the same when x was 0, then we could say that this function is continuous. And the way that would show up on the graph is the two pieces of the graph would connect at x equals 0. And that would be at x equals 0 because that's where the break is in this function. Okay, so we're going to analyze a couple of these graphs here. Kind of a quick and easy way to tell whether a graph, if you've got a graph to look at, to tell whether the graph is continuous is just to say, well, can I put my pencil down on one part of the graph and then continue drawing the whole thing without ever having to pick my pencil up? Now for this one here, I kind of want to go through that because there's some interesting things to look at on this one. Use that color. Okay, so if I could go out to -infinity over here and get to the edge of this graph, I would be able to continue drawing all of this, all of this, all of this, up until I get to this point right here. And that's an open dot, which means anytime you have an open dot, you'd actually have to pick up your pencil. So I'd have to pick up my pencil there, so I could say that this is now not continuous at this particular x value. That would be an x value of 0. I do want to kind of talk about the rest of it, though. We've already determined it's not continuous, but let's deepen our knowledge a little bit here. So if I continue drawing over here, I could draw from this point to that open dot, but then I'd have to pick my pencil up again because the open dot means that part is not included. So it would be discontinuous at 1 as well. Then right on the other side of that dot, I could continue drawing, and I could draw completely until I get to that last dot there. And that last dot actually indicates that that's the end of the function. It is an open dot, so again, it's not included, but I could say that it is continuous between 1 and 3, 2, 3, 4, 1 and 4, and it's continuous between 0 and 1. And it's continuous between -infinity and 0. So because it's not continuous forever on its entire domain, I would have to say that this one is not continuous. To determine whether or not it's a function, I would use the vertical line test that we learned a couple of days ago, or reminded ourselves, really. I'm pretty sure you guys already knew it. So using the vertical line test on this one, there is no place on this graph where I could draw a vertical line and it would intersect the curve of the function more than one time. So that means it passes the vertical line test of functionality and therefore is a function. And lastly, we want to state the domain and range. Okay, so for this one, the x values for this first piece go from -infinity to 0. I think I'll make some notes down here at the bottom. In fact, I think I'm going to do this with a number line because I think it shows things very nicely. So I'm just going to kind of match the number line up with the graph that I have here. So 0 would be right here. There's some other interesting things happening here at 1, at 2, and then at 4. So I'm going to go ahead and put 2 more ticks there and put a 4 over there. The things on the left here, all of the x values are all of the x values are included. It won't let me undo that. Wow, crazy. Okay, anyway, I didn't even know I could do that. So learning something new. All right, so I'll go ahead and put in a few more tick marks over here, but I'm not going to label them because there's not really anything super interesting happening on this side of the graph. When I'm talking about the domain on this one, though, I would be going forever to the left. So everything over here, all the way up until I get to 0. Then at 0, for this piece of the function, there is an open dot. So I'm going to go ahead and put an open dot right there. Now for the next piece, there's a closed dot at 0. So if I put a closed dot on top of this open dot, it would have the effect of filling it in. And then it is continuous. There's a line drawn between 0 and 1, but then at 1, there's an open dot. So I'll put an open dot here and color in everything between. All right, next, between here and there, well, there's a closed dot at 2, and the function is continuous between those. It's connected with a solid line. And then between 2 and 4, there's a solid line, but at 4, there's an open dot. So I'll put an open dot there. So when I'm giving the domain for this one, I would need to describe everything that I see here. So the furthest left that I see it going is -infinity. So I would start with that, -infinity. And then that includes all of the x values up through this solid dot and all the way to this open dot. But at the open dot, there's a break. So I would put 1, the x value at the open dot, and close it with parentheses. And then I'll say union, because on the other side of 1, it picks up again, and it is continuous then from 1 all the way to 4. So I would use parenthesis to not include the 1. And then at 4, it was an open dot as well, so I would close parentheses there. So that would be my entire domain. I'm going to do this similarly with the range, but this one I'm going to build vertically so that it matches up with the graph nicely. Let's see if I can get rid of some of my markings here to make it so that's not so much junk on my picture. Oh, that's much better. Okay. All right, so I'm going to use a green pencil this time. And I'm going to draw a vertical line over here. And I'm going to match it up with the y-axis. So this would be where 0 is on my y-axis. And let's see, I guess I'll start from the top because I can see everything that's going on up there. At the very top of my graph, I have an open dot, and that's at 4. So I'm going to give myself a difficult time trying to draw this, apparently. Okay, so 1, 2, 3, 4, just matching it up with my graph here. So at 4, there's an open dot. And then from the open dot, it goes downward, and this actually goes downward forever. So just with that one little piece of the graph, I could continue. I could draw an arrow going downward, and it includes everything between that open dot and negative infinity. Now, if I put in the other pieces of the graph here, this piece here includes an x value only of 2. So that would just give me a solid dot at 2. This little piece here gives me an open dot at 2, but if I draw an open dot around a solid dot, it's still solid. And then a solid dot at 1, and then it includes everything in between those two. And this last piece just includes 1. Now this extra piece that I drew on here is just a part of what I already had drawn. So I can actually just state the range just by looking at what I had colored in originally there from looking at that very first piece of the graph. And for the range, I want to look at it from least to greatest. So I'm looking bottom to top here. I've got an arrow pointing downward, which means it goes to negative infinity. And then it goes all the way up to 4. So 4 would be my, my top number there for my range. But it is an open dot at 4, so that's going to be a parenthesis, which means it gets infinitely close to 4, but doesn't actually get there. So the second example that we have here, oh, these are guided practice problems. Anyhow, so go ahead and do that guided practice problems. You're going to pause the video here, and then you can come back and see how you did on it. Okay, so welcome back. You should have gotten that the first one was not continuous. It has a break when x is 1. It is a function because it does pass the vertical line test. The domain is all real numbers because the graph does go forever to the left and forever to the right. And the range is from -4, including -4, because we have a solid dot there, to a positive infinity because it does go upward forever. All right, next up, we're going to be evaluating a piecewise defined function. So to evaluate a piecewise defined function, first I want to get familiar with my function. It is called f of x, and f of x is defined as x minus 4 for x values that are less than -1. So if my x value is less than -1, then I'll use this as my f of x value. And f of x is defined as 3x minus 1 if the x is greater than or equal to -1. So if my x value is -1 or something bigger than -1, then I'll use f of x equals 3x minus 1. So here we go. For our first example, we're asked to evaluate f of x when x is equal to -3. So I'm going to start off by writing that in my function notation there. So f of -3. That means find f when x is -3. And then I have to determine which piece of the function I should use. So to do this, I'm actually going to use a number line. And I'm going to break up my x values according to what they say for the x's in my function. Okay, so I'm going to say 0 is right here in the middle. So this is -1, -2, -3. And this would be 1, 2, 3. That -3 turned out really bad. There we go. Okay, so I'm going to use some color coding here also because I think it helps you see things. So this part here says when x is less than -1. So since it's a less than, not equal to, I would put an open circle there at -1. And the less than sign, remember the arrow points which way you're supposed to shade for that. So this would be everything over here. And then I'll use maybe this bright green, turquoise, whatever it is, for the other side. So for the other side, it says for all the x's that are greater than or equal to -1. So that would be a solid dot at -1. And then again, the arrow points to which side you're supposed to shade on that. So I'm going to shade this one to the right. And so if the number that I'm given falls in the green zone, then I'll use the green one, this one here. And if it falls in the pink zone, then I'm going to use the pink one, which would be this. Okay, so taking my first number here, f of -3, I'm going to look where x is -3. That's right here. That falls in the pink zone. So that means I would use the pink equation up here. So I'm going to be using f of x equals x minus 4. I'm going to write that up top here. As down here, I have to actually put in the -3 for x. So this would say -3 minus 4. And so my f of -3 would equal -7. For my second one, it says to find the value of f of -1. I think I'll do this one in a different color. Let's use a green. Okay, so this says when x is -1. That's what it's asking for. So I have to figure out which piece to use. My pen is going to be laggy now. That's fantastic. Okay, that says use f of x equals, and then we have to figure out which piece we would need to use. So I'm going to go to where x is -1, which is right here. And I notice I have both green and pink there at -1. But the pink is an open circle and the green is a closed circle. And open means not included, closed means included. So for this one, I'd actually be using the green one. So I'm going to be using 3x minus 1. So down here, I'll say f of -1 is equal to, and then I'm going to be using 3x minus 1, but I have to replace the x with -1. So this would be 3 times -1 minus 1. And then following order of operations from here. So 3 times -1 is -3. -3 minus 1 is -4. So I would say f of -1 is -4. Alrighty, on the next page on your notes there are some guided practice problems. So this would be another place where you need to pause the video and then come back and see how you did. Okay, welcome back. So you should have gotten f of 0 equals -1, g of -3 equals -10, g of 3 equals -9, and f of 5 also equals -9. Now, if you missed any of those, you need to mark those down as one that you need to look at again. And then if you still can't figure out why, there's some color coding on here, by the way, in case you wanted to watch this again. You need to make sure you come and ask in class tomorrow.